Assalamualaikum. In this session, we are going to look on how to design a compression members. To design a compression members, there is a few steps that we have to follow. So this slide presenting the design step in designing a column. Start with identify the geometry properties, and then we check the slenderness ratio, followed by identify the grade stresses of selected species timber, and then we got to identify the K factors value. And then from it we may calculate the stress applied on column and calculate stress allowable for the selected sections and selected timber species, and from it we may do an evaluations of the column. As a start, we have to identify the length of column, referred as L, and then we identify the effective length, which is LE. We got to identify the area. You also have to identify the IXX, IYY, radius of gyrations, and the Z value. After identify the geometrical properties, we get to find the slenderness ratio, okay, where the slenderness ratio is equivalent to lambda is equivalent to LE divided by radius of gyration, where if we found that the slenderness ratio is less than 180, so the K value that we are going to use is K1, K2, and K5. But in case the slenderness ratio value is less than 250, so the K value that we have to use is K1, K2, K5, and K8. And the same things goes if our K is greater than 250. Next, we have to identify the grade stresses of selected timber that we choose to use for our project. So the grade stresses can be identified from table 1, 2, and 4. Okay, but we have to identify the moisture content of the timber species first, followed by identify the timber species, and then we got to identify the grade of timber that to be used, either it is selected, standard, or commercial species. So for timber column design, we got to refer to a column of compression parallel to grain. The next step is we have to identify the K factor. So as to before, the K factor related to the column design is K1, K2, K5, and K8. So K1 is the durations of loading, can be identified from clause 9, page 19, table 5. And then we have K2. K2 is a load sharing system. If load sharing is less than 4 members and spaces between members is less than 610 mm, so K is 1.0. If more than 4 and the spaces is more than 610 mm, so K will be 1.1, where K5 is equivalent to 1.18 for solid circular section, and if it is a square section, the K5 value is 1.41, but for rectangular section, K5 will be 1.0, and K8 can be obtained from table 10, page 29. After getting the value of K factor, then we can calculate the stress allowable, where the stress allowable is equivalent to stress compression of timber multiply with K factor. After identify the stress allowable of a timber, then we may start calculating the stress applied, where the stress applied is equivalent to P over A, where P is the pressure applied and A is the area section. After identify the stress applied and stress allowable, we got to check the satisfactions of design, where the design will be considered as satisfied design when stress allowable of column is greater than stress applied. Just in case if the stress applied is greater than stress allowable, so we got to change the dimensions of timber or the species of timber. Okay, in this session, let us look on an example on how to design a column. Okay, say we have a sections of timber, okay, in the size of 150 mm and 60 mm. Okay, say the column, okay, is a pin column, and the length of column is 3 meter. The clear height of column is 3 meter. The column is carrying a design load P of 40 kilonewton. Okay, so for timber species, it is selected to be cengal, and it is for a long term design, and the moisture content is less than 19%, and is grouped as a standard groups of timber. Okay, so start with identify the geometry. Okay, the geometric properties. Okay, so from this figure we can find that the length of column is 3 meter. Okay, the effective height LE, okay, of column can be determined from table 9. Okay, so this is table 9, effective length of compression members. So since our column is pin column, so it is considered as restrained at both ends, in position but not in direction. So the effective length was calculated by using this value, which is 1.0. Okay, so 1.0 times L will be the LE, the effective length of column. Okay, so say this is 1.0 times L. L is 3 meter, so our effective length is 3 meter. Okay, and then the B of beam is 60 mm. The H of beam is 150 mm. Okay, so instead of that, we have to identify the IXX, second modulus of inertia, which is using the equations of B H the power of 3 divided by 12. Okay, which gives us a value of 60 times 150. Okay, power of 3 divided by 12, we get a value of 16.87 to the power of 6. Then we also get to find the value of IYY. Okay, IYY is HB square root divided by 12. Here we have 150 times 60 to the power of 3 divided by 12, which is give us a value of 2.7 to the power of 6. Okay, next we have to identify the radius of gyration, which is small ixx. Okay, and the equation used to identify the radius of gyrations is b divided by square root 12. Okay, so from this equation we can find the value is 60 divided by square root of 12, and then which gives us a value of 70.32. Okay. Alright, next step is we also have to find the value of Z. Okay, the value of Z. So Zx is equivalent to BH squared over 6, since this is a rectangular section. Okay, from the calculation, which is 60 times 150 to the power of 2 divided by 6, we get the value of 225 to the power of 3. Okay, and finally we get to find the area of section, which is B times H, 60 times 150, and from it we get a value of 9,000 millimeter square. Okay, so this is the geometry properties of the timber that we have to identify before we can start calculating the or checking the section, either it is satisfied to carry the load or not. Okay, next step, we have to identify the slenderness ratio. Okay, we got to identify the slenderness ratio. The slenderness ratio of column is given by using an equations of LE over IYY, radius of gyration. Okay, so from it we get a value of 3000. Our effective length is 3000 divided by the radius of gyration, which is 17.32, and it will give us a value of 173.2, and from it we identify that the value is less than 180. Okay, so since it is less than 180, it's considered as a short column where we do not require any K8. So the next step is identify the grade stresses of selected timber. So in our case, since we are using cengal, so we have to look on cengal timber. Okay, cengal, and the moisture content is less than 19%, and it is under dry grade, and it's grouped as standard timber. So by refer to table 2, since it is a dry grade, which is the moisture content is less than 19, so the timber is considered as dry grade, and let us find the timber of cengal. Okay, so from timber 2, from table 2, okay, we can see this is the value of cengal, and we refer to column compression parallel to grain because we are designing a column. So we drag out here, we look on the STD, okay, which is standard group, and the value of dry grade stresses of compression member of cengal timber is 25, right? 25.1. Okay, so from the table we found that the grade stresses of cengal timber is 25.1 Newton per millimeter square. Okay, the next step is we have to identify the K factor. Okay, the K factor. Since our timber slenderness ratio is less than 180, so the K factor related to our design is only K1, K2 and K5. Okay, based on the Malaysian standard requirement, we can find that the value of K1, K2 and K5 is 1.0. Okay, because since our design is a long-term design, K1 is referred to durations of building, okay, durations of loading. So K1 is 1.0 because our design is a long-term design. Okay, for K2, since our design is only a single column, so it's considered as 1.0. And for the form factor, okay, form factor, here we have K5 for form factor. 1.18 is for solid circular, 1.41 is for solid square section. Since our section is a rectangular section, so K5 is equivalent to 1. Okay, so from the Malaysian standard, we can find that all the K is equivalent to 1. Okay, K1 is 1, K2 also 1, and K5 also 1. Okay, From the value, we can calculate the stress allowed. Okay, stress allowed. Okay, stress allowed, where the stress allowed is referred to a value of grid stresses, which is 25.1 times all the K, which is 1.0 times 1.0 times 1.0. So stress allowed by Chengal is about 25.1 Newton per millimeter square. Okay, as referred to the stress applied. Okay, as referred to the stress applied, now we can calculate the stress applied. Okay, just now we are calculating a stress allowed. Now we are calculating a stress applied. Stress applied is equivalent to P divided by A. Okay, since we have P is 40, okay, to the power of 3, we have to convert it from kilonewton into Newton. Divide by A. A is 9,000 millimeter square. We get the value of 4.44 Newton per millimeter square. Okay, by referring to the value of stress allowed that we have been calculated before, compare with the stress applied, we can find that the stress applied is less than stress allowed. Okay, because stress applied is only 4.44, while the stress allowed is about 25.1. So from this finding, we see that the value of stress applied is less than stress allowed. So we can make a conclusion to say that our section selected is satisfied the design requirement. Right? Thank you. Okay, now let us look on the second example where the column is having a value of K8. Okay, say we have a column. Okay, now we are dealing with rectangular or square column, which dimension is 70 mm times 70 mm. Okay, and the column's height, okay, or the length of column, say to be 4 meter. Okay, it is a pin support column. Okay, say we select Kempas as a species of timber, and it is a selected timber where the moisture content of the timber is greater than 19%. So it is considered as a wet grid, and the structure was designed for long term. Okay, so start by identify the dimension properties. Okay, as we can see, the L is 4 meter, the LE or effective length is 4 meter times 1.0, since it is a pin support, so the effective length is 4 meter. Okay, and then the radius of gyration IYY, which is B over square root 12. Okay, since our B is 70 mm, so 70 divided by square root 12, okay, which gives us a value of 20.20. Okay, the area of section is 70 times 70, which is B times H. We got a value of 4,900, okay, millimeter square. Right, so after get the dimension, okay, we get to identify the slenderness ratio. Right, slenderness ratio of the structure selected. Okay, slenderness ratio is referred to lambda is equivalent to LE over radius of gyration IYY. So here the value will be 4000 divided by IYY, which is 20.20. That gives us a value of 198. In this case, the slenderness ratio is greater than 180 but less than 250. Okay, greater than 180. So we require a value of K8 in the design of column. Okay, since we require K8, we have to find the K value. So the normal K value used for column design is K1, K2, K5, and in this case, K5, and in this case we require K8 as well. So from the MS, we can see that the value of K1 is 1.0 since this is for long durations. K2 is also 1.0 because it is a single column. And then we have K5. Okay, K5. Since it is a square column, the K5 value is 1.18. Okay, K8 you can get from table 10. Okay, you can identify K8 from table 10. Okay, so in order to use table 10, right, let us look on the table 10. So this is table 10. Okay, so in order to use table 10, you have to identify the value of, the first step is you have to identify the value of, okay, slenderness ratio, which is LE over radius of gyration. Okay, you get to find the slenderness ratio, LE over radius of gyration. Okay, so from the calculation of slenderness ratio that have been carried out before, we found that the slenderness ratio of our case is 198. So here the value 198 is not available in the table, but the value available is 180 and 200. Mean to say that we have to do, okay, interpolations, okay, to identify the value of K8 for slenderness ratio 198. Instead of that, you also have to find the value of E divided by stress of the timber. Okay, stress of the timber. Right, so E is already given in table 1, since our moisture content is greater than 19. So we got to find the modulus of elasticity. So from this calculation, the modulus of elasticity for compass, okay, let us look on compass. Okay, so this is compass. Okay, so this is a compass species, and we refer to selected compression parallel to grain, which is give us a value of 22.3. Okay, the grade stresses for compass for the compression parallel to grain is 22.3, and the modulus of elasticity is about 16,600. Okay, 16,600 is the modulus of elasticity for the compass species. Okay, so we have two values here, mean and minimum. So for our design purpose, we are using the mean value, which is 16,600. Okay, by knowing the value of slenderness ratio, which is LE over I, which is 198, and we know the value of elasticity over stress timber compression. Okay, we get a value of 16,600 divided by 22.3, which gives us a value of 744. Okay, so once again we refer to table 10. We try to find the value of K8. So in this case, we couldn't find a value of 744 because the value occurred is only around 700 to 800, and for the slenderness ratio is about 180 to 2000. So in this case, we have to do the interpolation. Okay, do the interpolation that we know that the area of K8 will be lies around this area. Okay, so by using the interpolation method, you got to find the K8. Right, hopefully you know how to do the interpolation. So from the calculation that been carried out, it is found that K8 is equivalent to 0.11. So please do some exercise to carry out the interpolation and find on how I'm getting the K8, which is equivalent to 0.11. Okay, by getting the K8, we can calculate the stress allowed. Okay, stress allowed by the timber species selected. Okay, so in this case, since compass stress, grade stress is 22.3, so we multiply with K1, which is 1, K2, which is 1, and then K5, which is 1.18, and finally we multiply with the K8, which is 0.11, and which gives us a value of 2.89 Newton per mm squared. So this is the stress allowed by the compass species of the section selected. Now we can find the stress applied, where the stress applied, okay, stress applied is equivalent to P over A. Okay, from the question we found that P is 4000. Okay, P is 30. Okay, P is 30 to the power of 3 in order to change the unit from kilonewton to Newton per mm. Kilonewton to Newton, multiply with area. Okay, where the area is 70 times 70. We found that the value of stress applied, okay, is 6.12. So in this case, we found that the stress applied is greater than stress allowed. So shows that the section given is not satisfied. Okay, not satisfied the design requirement. So in this case, we have to change the dimensions of timber, okay, in order to identify or in order to satisfy the design requirement. Instead of changing the size of specimen, we may also change the timber species, okay, or maybe we can change the timber grade as well. Okay, so this is the example of how to identify the K8. Thank you.